Welcome to ShowOffer.io. In today's system design, we are building a web service that helps customers buy the cheapest available copy of a book from a network of online booksellers. Here's how it works. A customer submits a purchase request with three things: the book title, their shipping and payment information, and the maximum price they're willing to pay. Our service then reaches out to many booksellers in parallel. If any of them offer the book at or below the user's price, we go ahead and buy the cheapest one automatically, and later tell the customer which seller was used and for how much. If none of the sellers meet the price cap, they still respond with the lowest price found, so the customer can choose whether to retry or wait. To keep this design grounded, we'll make a few simplifying assumptions. Book titles are globally unique. Think of them like product IDs. Each purchase is for just one copy of the book. Sellers may or may not all sell the same books. Prices vary by seller. And finally, sellers expose different API formats, so we'll need to handle heterogeneous protocols. This gives us a rich and realistic foundation to explore performances, concurrency, and resilience in a high FANG system. Now, without the introduction, let's walk through the core requirements, starting with the functional side. Functional requirements number 1, submitting a purchase request. As a user, I want to request a book by providing the title, my shipping and payment information, and the maximum price I'm willing to pay. This kicks off the entire resolution flow in the backend. Functional requirement number 2, retrieving the price resolution. Once I've made the request, I want to know whether the system found the seller within my budget, or at the very least, what is the lowest available price was. This gives user transparency, even when no match is made. And finally, functional requirement number 3, triggering an automatic purchase. If a seller's offer meets my criteria, I want the system to go ahead and buy the book for me automatically. No extra confirmation step needed. That is how we deliver a seamless shopping experience. Now on to non-functional requirements, ranked by what matters most in the system. 1. Efficiency. We want to avoid unnecessary work and minimize the cost of each request. This means things like calling the fastest seller first, reusing cached results, deduplicating duplicate results, and skipping over the unstable sellers, especially since we are calling each seller directly without adapters. 2. Latency. So the entire process should resolve quickly, ideally within 5 seconds at the 19th percentile. 3. Idempotency. We must avoid double charges or repeated purchases if the same request is retried. 4. Scalability. The system should handle up to 200 QPS, and that can translate up to 20,000 seller API calls per second during finding out at peak load. 5. Reliability. Even if some sellers are slow, down, or flaky, the system should keep running and return partial results if needed. And number 6, observability. We need full traceability for each request, including the internal logs, error metrics, and seller call performances, to help debug and optimize the system later. Let me take a little bit about why we rank the priorities of the non-functional requirements like this. We rank efficiency highest because the system core value is to help user find a cheap price fast, and that means minimizing the unnecessary work like exiting early, prioritizing high-value sellers, batching calls, and deduplicating in-flight lookups. Latency is the next, as timely responses drive user trust and satisfaction. Idempotency came third, because the system involves real purchases. Without safeguards, retries could trigger double charges or duplicate orders. Scalability is essential to handle the peak traffic and final volume. Reliability ensures users still get the useful results even when sellers fail. Observability, while operationally critical, has the least direct impact on the user experience and can be layered in the post-MVP. So during your interviews, not all the non-functional requirements needed to be discussed within those 40 minutes. Get alignment with your interviewers to prioritize show your seniority. Now let's talk about the high-level design. During your interviews, we strongly suggest you put the API design and entity list in this part, and each part of the high-level design end-to-end should illustrate one functional requirement, including what is the data flow, what is the building block, and their functions. In addition, expand entity schema if needed. Let's start with the functional requirement number 1, submitting a purchase request. This is handled by a simple HTTP endpoint, post-purchase request. In the request, the user provides 3 things: the book name they want to buy, the maximum price they are willing to pay, and their customer information, which includes the shipping address and payment details. Here's what a real example looks like here. Book, designing data incentive applications. Max price $30, plus address and credit card information. In response, the system returns a unique request ID and a pending status. That means the system has accepted the request, but it hasn't yet resolved which seller to buy from. That comes later. So this is an asynchronous API. We don't wait to fetch seller offers or perform the purchase immediately. Instead, we handle that in the background and let the user pull or the webhook for using a separate endpoint. That will be covered in functional requirement number 2. Now let's look at the entities involved. First, we have the user, the end customer making the request. Second, the book, treated as a unique identifier like an ISBN or title. And finally, the purchase request. This is the heart of the flow. It tracks the book, the user's price cap, and the current situation resolution status, whether we found a match, made a purchase, or not. Together, these 3 entities are all we need to get started. Now let's move to our design diagram to illustrate the end-to-end working solution as a workflow. Again, this is not optimized, but it can be a solid foundation to start with. Step 1. API gateway receives the post-purchase request call and forwards to the backend service. Step 2. Request handler service performs validation of the input fields, for example, the price format, the required fields, the generation of the request ID as well. Step 3. The persistence of a new purchase request entity into the database with the status pending. Step 4. The same service includes a message with request ID into the internal request queue. For example, it can be Kafka, SQS, PubSub. This can be discussed later. Step 5. The system returns a 202 accepted response with the request ID to the user. The actual resolution, like the seller find out and purchase, happens asynchronously. That will be covered in the next functional requirements. Now let's move on to functional requirement number 2, retrieving the result of the price resolution. Once a user submits a purchase request, they can call get request status and pass in their request ID. This is a polling-based API, meaning the client periodically checks if the request has been resolved. For sure, you can leverage webhook in the later discussions, or you can reference to our webhook design in ShowOffer.io. So there are 3 possible outcomes. Success. If a seller was found within the user's price cap, the response returns. Status equals to success. The resolved price and the resolved seller. For example, Booktopia at $24.99. Second, if no seller meets the price threshold, the response says status equals to not available, and it includes the lowest available price across all sellers, so the user still gets the value. And if the system is still resolving, maybe we're still querying sellers and retrying, the response simply returns status equals to processing. This gives the user full visibility into the request lifecycle without blocking on the seller lookups or purchases. The actual purchase, if needed, is handled separately and automatically, as we will cover in the next functional requirement. Now, let's take a look at entities that support this resolution flow. First, we continue using the same purchase request object. This now checks more than just the original user request. It also holds the status and the final outcome, whether we're still processing, found a successful offer, or didn't find anything under the cap. Next, we introduce the seller offered entity. This represents the actual response we got from each bookseller, including the price they offered, whether the book was in stock, their latency, and other normalized metadata. And finally, there's the bookseller entity, which is key to managing heterogeneity. Since each seller exposes a different API with different formats and protocols, this entity stores per seller configuration. For example, the API endpoints, the request templates, the response mappings, the retry policies, and quality scores like latency or success rate. So this gives our system enough context to talk to dozens or even hundreds of the sellers cleanly. Let's come to our design diagram for functional requirement number 2 based on the previous functional requirements. Here's our workflow. So once the purchase request is enqueued from the functional requirement number 1, the system kicks off seller resolution via a backend worker. So step 1, the final worker consumes the request ID from the request queue. It retrieves the associated purchase request and book name. And step 2, the final worker queries each external bookseller public API directly using seller-specific config from the bookseller table in the database, and it constructs the HTTP requests like the URL, headers, payload using the seller's metadata. It sends the HTTP request and parses the response based on the expected JSON format, and each call returns a normalized tuple such as seller ID, price, availability, and inventory. And step 3, the final workers filter out unavailable or overpriced offers. It selects the cheapest seller whose price is within the user's max price. So step 4 truncates into 2 parts. The first part about step 4a, if the valid match is found, the worker updates the purchase request with the status equal to resolved, they resolve the price and resolve the seller, and proceeds to automatically trigger the purchase in the next functional requirement. But what if it's failed or not meet the price? The worker updates the purchase request with status equals to not available and the lowest available price from all seller responses. And finally, step number 5, users poll get request status to retrieve the final outcome. If the status is resolved, show match the offer and the price. If status is not available, return lowest available price as fallback. And again, this part from the polling can be also used from the webhook. Now let's talk about the functional requirement number 3, the final step in our purchase flow. Once the system finds a seller offering the book at or below the user's max price, it should automatically trigger the purchase without waiting for additional confirmation. This flow picks up right after the functional requirement number 2, when the request status becomes success. And at this point, a background worker takes over and calls the seller purchase API directly. For example, let's say Booktopia offered a book for $12.5. Our system then issues a request like this, the post HTTPS api.booktopia.com/purchase. with a request body containing the ISBN of the book, the agreed price, the user shipping information, their payment token, and a reference ID to check the purchase, such as the original request ID. The purchase logic is handled by the same worker that performed the find out and price resolution, ensuring a tight handoff and minimal delay. Because the seller APIs vary wildly in format, this worker also handles response parsing and normalization, so we can track success, detect failures, and report back to the user consistently. Let's check out the workflow in our design diagram. Step 1. Find out worker from the functional requirement number 2 selects the best valid offer from the seller responses, where price is less or equal than the max price. Step 2. Final worker initiates a direct HTTPS call to the selected bookseller's purchase API, using the configuration stored in the bookseller entity. It builds the HTTP request using the API endpoint, the HTTP request methods, the headers template, and the request body template. For example, it has the dynamic fields like the ISBN, pricing, shipping information, etc. Step 3. The final worker sends the request to the external seller system, handles retries, parses the raw response, and normalizes it to the exact, like order ID, final price, delivery ETA, or error code on messages. And step 4, the return. If it is all success, the worker updates the purchase request with status equals to success, and resolve the price, resolve seller, purchase timestamp, etc. If it's on failure, the system may retry, attempt the next best offer, if any, or mark the request as purchase failed based on the business rules and the error type. To recap, this is a fire and forget purchase model. The user doesn't need to reconfirm. As long as the offer is valid and within the budget, the system completes the purchase on his behalf. If the purchase succeeds, we update the request to success and log the seller, final price, and timestamp. If it fails, due to the timeout, rejection, or payment issue, we may retry, fall back to the next best offer, or return a purchase failed status instead. And this design helps deliver fast, seamless purchase experience and let the system handle edge cases intelligently in the background. Now let's go deeper into one of the most important parts of our system. How do we make find out efficient and cost effective? Remember, every user request might contact up to 200 sellers. If we find out blindly, we will overload our system, rack up unnecessary costs, and hit latency issues. So in this deep dive, we will walk through 3 strategies to eliminate waste and speed things up. Strategy 1. Early exit once a valid price is found. The idea here is simple. As soon as one seller replies with a valid price, there's no need to wait for the rest. We just go ahead and buy. Let's say a user sets a max price of $30. The system starts calling sellers. The first few sellers don't match, but then one responds with an offer at $28. That is great. We stop the find out early, trigger the purchase immediately, and cancel or skip the rest. This improves latency and reduces cost because we are not waiting for every slow or unreliable sellers. Of course, there is a trade-off. We might miss a better deal from another seller who replies later. But that's the business decision. Do we want fast enough and cheap enough, or absolutely lowest price with added delay? We can always fine-tune this by adding a grace window, like waiting 200 milliseconds more, only exiting early if the price is significantly below the user's cap. Strategy number 2. Adaptive find out with seller tiers. Instead of calling all sellers at once, we group them into tiers. Tier 1, fast, reliable sellers with good prices. Tier 2, okay sellers. Tier 3, long tail or flat key ones. We first query tier 1, the best bets. If no valid offer comes back, only then do we escalate to tier 2, then tier 3. This avoids wasting time and money on sellers that rarely give good results. To support this, we maintain a seller rank engine. It tracks seller performance metrics like success rate, response latency, price competitiveness, inventory accuracy. And based on this, we refresh the tiers regularly, maybe hourly or daily. In this way, we adapt to changing seller behavior and always starts with our best valuable partners. Strategy number 3, cache valid offers to avoid redundant costs. The third strategy is caching, which also benefits our end-to-end latency requirements. Let's say seller A just sold us 10 seconds ago, and they have the book X for $25 and 500 copies are available. If another user asks for the same book right now, do we really need to call seller A again? Probably not. Instead, we store that response in a book offer cache, a lightweight, short-lived memory store like the Redis. When the next request comes in, we check the cache first. If the cached offer is recent enough, say like under 60 seconds, still under the user's max price, and has enough inventory, then we just reuse that offer, no extra API call needed. And of course, to avoid the issues, we need to set tight TTLs and only cache sellers with stable inventory and always reevaluate before the final purchase, just in case the price has changed. And this cuts on the duplicate work, protects users from spammy traffic, and boosts our system throughput. Now let's walk through the changes added in this deep dive 1 diagram to improve our final efficiency. First, in purple color, we've implemented strategy 1, exit early. Find-out workers now pass seller responses to a centralized find-out controller. As soon as a valid offer is found, meaning the price is under the user's max, the controller immediately signals other workers to pause or skip remaining requests. This avoids unnecessary calls and reduces latency. Next, in green, we add a seller rank engine, which powers strategy 2, adaptive find-out. It maintains a tiered classification of sellers from tier 1 to tier 3, for example, and tells the controller who to query first. This helps us prioritize fast, reliable sellers and defer or skip low-quality ones. Finally, in the orange color, we enable strategy 3, cached offers. Each time a worker gets a valid response, it writes it to the book offer cache. Later final requests can reuse the recent offers if the price and the inventory still look good, avoid redundant API calls to the same seller. Together, these 3 strategies form the core of a smart, cost-efficient find-out system. Now let's move on to the deep dive number 2, where we solve a very real problem. What happens when many users request the same book at most the same time? If we simply process each request independently, we might find out multiple times to the same 200 sellers, do redundant work, and even worse, accidentally double purchase the same exact offer. So Deep Dive 2 introduces 2 key strategies: deduping requests and making purchase idempotent. Strategy 1, coalesce duplicate lookups. The first strategy is all about avoiding redundant find-outs. Imagine 3 users all ask for the book, designing data incentive application, for example, all with a max price of $30. Within 1 or 2 seconds, instead of launching 3 massive find-outs, we detect that these requests belong to the same group, same ISBN, same price bucket, and we collapse them into a single resolution. Behind the scenes, we keep a small in-flight registry keyed by ISBN plus max price bucket. When a real request arrives, if nobody is resolving this book yet, start a new FindOut. If FindOut is already running, just attach the user to that group. When the lookup finishes, everyone gets the same answer, either the winning price and seller or the fallback lowest price. This makes the system far more efficient during the busy periods. Strategy number 2, idempotent purchasing for safety. So even after deduping the lookups, users may still end up trying to buy the same seller offer. So our second strategy ensures we never double purchase, while still allowing safe parallel buys when inventory is high. We start by generating a purchase idempotency key, like hash function within the ISBN, the seller ID, plus the price. If another worker is already purchasing the exact same offer, we simply reuse the result, success or failure, instead of making another charge. But what about sellers with large inventory, like 100 available copies? We want to allow multiple purchases in parallel for different users. To support that, we add a small sequence number to the idempotent key. This lets each user safely purchase their own copy while still preventing accidentally double buys of the same exact unit. Finally, right before purchasing, the worker performs a quick revalidation, just to make sure that the price or inventory hasn't changed since the FindOut response. This protects us from overselling or buying at an outdated price. Now let's walk through the updated diagram for deep dive number 2. We've added 2 key strategies, and you can see from the color coded, purple for the strategy 1 and green for the strategy 2. So starting from the strategy 1, deduping the requests, we've introduced a new component called dedupe registry. This acts as a short-lived memory that keeps track of the in-flight resolutions. When the FindOut controller gets a request, it first checks its registry. If a lookup for the same, for example, ISBN plus price bucket is already active, it joins the group and waits for the result. If it's not, it starts a fresh resolution and writes into the registry with a short TTL, just say 3 seconds. This prevents redundant FindOuts when many users request the same book in a short burst. Now moving on to strategy 2, idempotent purchase logic. We've added a green color path for the safe purchasing. When a valid offer is found and the worker is ready to buy, it generates an idempotent key using the book ISBN, seller ID, and price. It then checks the idempotent log store. If the key is already held, the worker knows this purchase is already in progress or complete and can reuse the result. If the lock is free, it proceeds to purchase. And to support the safe parallelism, we also added a parallel sequence handler. If the inventory is high, we attach a sequence number to the idempotent key so the multiple users can buy without conflicts, while still respecting the inventory limits. And finally, before any purchase is made, we added a revalidation step that queries the seller again for the latest price and inventory, just to be safe. Now let's explore deep dive number 3. How do we prevent overload in a high FindOut architecture? So each user request could find out up to 200 sellers. So under the high QPS, this can quickly stream both our backend and external seller APIs. This is about the rate limiting, also about the politeness in sending requests to external websites. We use 2 key strategies here to stay stable under the pressure. Strategy number 1, throttle FindOut admission. We introduced 2 new components to manage the concurrency. 1, throttling controller. It checks whether a request is allowed to proceed based on the real-time system limits. It can enforce caps like 500 total concurrent seller calls or 50 calls max to any individual sellers. It also adapts dynamically based on the error rates and the latency spikes. 2. Final admission queue. Once approved, the request enters this queue and waits its turn. It smooths our bursts and prevents the sudden overloads. And the flow works like this. The final controller first sends the request to the throttling controller. If approved, it enters the queue. And from there, a final worker eventually picks it up and executes the seller API call. This gives us a fine-grained control over how many seller calls are in flight at any given time. Strategy number 2. Global rate limiting by user, seller, or region. This strategy applies cross-cutting rate limits to guard against abuse or traffic spikes from the specific sources. We add 2 more components here. 1. Global rate limiting gateway. This sits in the request path and checks rate limits using the token or leaky bucket algorithms. It evaluates limits like no more than 10 requests per user per minute, no more than 500 QPS to seller B, or max 5,000 QPS per region. Second, rate limit store. The backend, backed by the Redis or similar, it stores the rate counters with TTLs and supports atomic updates. Before calling any seller API, the final controller checks with this gateway. If the rate limit is okay, proceed. If it is breached, we drop, delay, or degrade gracefully. Now let's work through the additions in Deep Dive 3 where we address system overload due to the high fan-out traffic. First, in strategy 1, the throttled fan-out admission, we added 2 new components in the purple. Throttling controller. This enforces a real-time concurrency limit, global or per seller. It gates which requests can move forward based on the system load. Final admission queue. A bounded buffer that holds eligible final requests. When full, we either drop, retry later, or prioritize high-value requests. Then in strategy 2, the global rate limiting, we added 2 green components on the seller API path. 1, global rate limiting gateway. So before each external call, it checks if the current request is allowed based on the user, the seller, or the region level quotas. 2, the Redis rate limit store. This stores counters and TTLs to enforce those quotas using token or leaky bucket logic. Only if a request passed both the throttling and rate limiting checks, it proceeds to the bookseller APIs. Altogether, this new path shields both internal workers and external sellers from overload, keeping the system stable under bursty conditions. So this is our today's content, and let's wrap up with a quick retro. In today's system design, we tackled a deceptive simple problem, buy the cheapest book. But under the hood, it required careful design to handle high fan-out to over 200 external sellers, low latency, cost control, and reliability, and smart protections against overload, duplicate purchases, and inconsistent data. We walk through the core APIs and async workflows, vertical breakdowns for each functional requirement, and deep dives into optimizations like early exit, request deduplication, and global rate limiting. Every strategy was grounded in real-world trade-offs, latency versus price, throughput versus cost, deduplication versus complexity. If you are preparing for system design interviews at companies like Databricks, Meta, OpenAI, or just want expert coaching and mock sessions, check out ShowOffer.io. We specialize in staff-level coaching, diagram walkthroughs, and targeted feedback. Good luck to your next interviews.